Imagine a hospital where an automated system is tasked with a critical job, scanning patient records to predict the onset of a life-threatening disease. To make those predictions, the machine learning model must first be trained on thousands of previous patient files, historical examples that serve as its textbook. The effort required to teach this model is dictated by the structure of those files, specifically how thoroughly each patient's history was captured when the data was originally recorded. Effectively, the machine's ability to forecast a future outcome is bound to the precision with which we documented the past. In probabilistic learning, the ideal scenario is what we call complete data. This refers to a dataset where every single variable relevant to the model is observed and recorded for every training instance. This is a data matrix for our medical model. It tracks age, blood pressure, cholesterol, and disease status. In a complete dataset, every cell is populated. There are no gaps, no missing tests, and no unanswered questions. When an algorithm is provided with a perfectly observed dataset like this, the process of teaching it becomes mathematically straightforward. Because every relevant symptom and diagnosis is visible in our patient records, establishing the relationship between them is a direct path. This flowchart shows the pipeline. When all variables are observed, the algorithm can calculate the likelihood of a disease directly from those visible facts. This allows the model to use maximum likelihood estimation. It's an optimization technique used to lock in the parameters of the model. MLE works here because it simply identifies the parameter values that best explain the facts we can see right in front of us. Complete data turns machine learning into a direct calculation because the algorithm never has to stop and guess the value of an unobserved variable. But real-world data collection is rarely that clean. Lab results get delayed, files are misplaced, or certain tests are never ordered at all. Consider a scenario where half of our training patients are missing their final disease status. Those missing entries break the straight mathematical line. The learning process is no longer a direct path, it's a maze. To calculate probabilities now, the algorithm must account for all possible values of that missing status. This forces the model to evaluate multiple alternate versions of reality, guessing the hidden states, rather than relying on a single observed fact. This is why a single hidden variable complicates the learning process. The model must navigate a sprawling web of possibilities instead of following the straight line of maximum likelihood. Outside of carefully managed research environments, datasets are almost always flawed. Information is lost to physical sensor failures, ignored surveys, or privacy restrictions that prevent us from seeing the full picture. Beyond technical glitches, some variables simply cannot be measured directly. A person's internal emotional state, or the underlying intent of a document, often remain hidden from observation. If we ignore these gaps and treat incomplete data as if it were perfect, we end up with models that produce confident but inaccurate results. Because the real world is rarely complete, probabilistic learning has adapted. This has led to the development of latent variable models, statistical architectures built specifically to handle datasets with hidden structures. These models manage a dual task. They must estimate the model's parameters while simultaneously inferring the values of the variables we couldn't observe. Complete data provides the baseline for how machines learn, but the broader challenge in modern modeling is developing the capacity to interpret the unobserved information that shapes our world.